Welcome to Eric Hurst's Training for Climbing podcast. Training for Climbing podcast. Training for climbing. Training for climbing. Training for climbing.
Hello, everybody, and welcome to the Training for Climbing podcast. I'm Eric Hurst from trainingforclimbing.com, and in this episode, we're going to continue our look at the bioenergetics of climbing and how you can train and climb more effectively with a better understanding of the topic of just how ATP, that's the fuel for muscular contraction, how is that produced in your muscles? How does it come about to power your climbing? It's a super rich topic. I've got some cutting edge information to present to you. It's really powerful information, especially for advanced and elite climbers. And there's a lot more we can build out in the coming weeks. Last month in part 1, we looked specifically at the anaerobic alactic energy system, which powers brief maximal movements. In this episode, we're going to look at the anaerobic lactic energy system. That is what enables you to sustain high power output for exercise or climbing that lasts, say, 15 seconds up to a minute or two. And then next month, we'll wrap up with a look at the aerobic energy system, which is important for powering more sustained, longer duration climbing that lasts many minutes or even hours if you're on a multi-pitch route or big wall. And also the aerobic energy system is important for driving the recovery process because much of the recovery between short bursts of exercise comes about by way of the aerobic energy pathway. So it's a ton of material. If you're new to climbing or a beginner or even maybe a couple years into the sport, these energy system podcasts may be kind of too much information, TMI as they say, because early on in the game you need to learn to climb and develop all the many mental and physical skills that will allow you to be a very efficient and effective climber. As you advance in the sport, well then strength and power and endurance and knowing how to train each of those attributes up becomes really critical to pushing your boundaries, pushing towards your genetic potential, which is likely higher than you think it is. And so it's exciting stuff, but if you put the cart before the horse, I guess you would say, if you're a new climber and you try to get into highly nuanced, targeted, intense training, it can have some negative outcomes in terms of injury or just leading you down a path of never developing high-quality climbing technique or mental skills and falling into the trap of trying to muscle through hard moves and such. But before we get to the nuts and bolts of energy system training, a few comments and thank yous. All of you who provided positive feedback on my first Energy System podcast. I really appreciate it. There were a lot of good follow-up questions, some of which I addressed in the first episode of Ask Coach Hurst. That's my podcast from a couple weeks ago where I answer your questions. And I'll be recording another episode of Ask Coach Hurst later this month. So if you want to submit a question, go to my Twitter feed, which is at train4climbing, and you'll see a post pinned to the top, and you can leave your question as a comment to that post, and hopefully you'll make the cut when I record the next episode of Ask Coach Hurst. Of course, I really appreciate it if you would share the podcast with your friends and partners, and if you're listening on iTunes, I'd really appreciate if you'd write a review, hopefully a 5-star review, to let people know more about this podcast. And the final thing before we get started, a shout out to my sponsors. There's a handful of companies that I've worked closely with, some for many years. And when I do presentations, clinics, and am out in public, I'm always keen to talk about the companies I work with and the great products they generate. I'm a performance-minded person, obviously, and so if there's a company I work with, it's not just on a whim. It's because I feel they contribute something to my performance and can help your performance. And so with that in mind, thank you to La Sportiva Shoes. I've actually been with La Sportiva since around 1990. So that's a long-term relationship, longer than a lot of climbing marriages, you might say. Also Nicros, who I've been with since almost their inception in around 1994. Maxim Ropes, DMM Whales, and Excalibur Distribution, Organic Climbing, chalk bags, bouldering pads, Friction Labs chalk, Rhino skincare products, and Cool, the climbing clothing company based out of Salt Lake City, makes some of the nicest outdoor and climbing wear around. Okay, now on to the good stuff. Let's get started. And this episode, number 2 of our look at energy systems and energy system training for climbing, we're going to drill down into the anaerobic lactic energy pathway and kind of get a sense of the strengths and weaknesses of this energy pathway. It's certainly a crucial one for climbers because, as I mentioned earlier, those high-intensity, nearly all-out efforts that last 15 seconds to a minute or 2 or 3 are largely powered by the anaerobic lactic energy pathway. And when you're engaged in one of those near all-out enduring efforts, it becomes painful. It becomes pumpy. Your forearms begin to balloon and the pain in your working muscles builds. And that's the hallmark of some of the metabolic byproducts and some of the limiting factors that come into play with this anaerobic lactic pathway. And we're going to drill down into all of those topics in this podcast. So you're going to have a better understanding of what's going on, say, in your forearms, in your climbing muscles, when you're getting pumped, and how you can best train to endure longer despite the pump, or hopefully avoid the pump and have higher power output and more fatigue resistance. Those are some of the things we're after when you do targeted training of the anaerobic lactic energy system, which, by the way, some people refer to as the glycolytic system or as anaerobic glycolysis, but the way I classify energy systems, or my lexicon, typically I talk about the anaerobic lactic energy system. And by the way, don't get that confused with the anaerobic alactic energy system, which is what we talked about 2 podcasts ago. The Atp-Cp energy system is alactic because it's high energy phosphates that yield instant ATP production without the generation of any lactate, hence the alactic name. This pathway, the anaerobic lactic, does result in a byproduct called lactate, which is a very interesting subject we'll talk about in just a moment. This podcast, there's going to be some information that I present to you that might be contradictory to what you've read in the past in magazines or maybe in high school or college biology classes. Perhaps what you've heard from other coaches, climbing or non-climbing, and I don't mean to be contradictory, and I'm certainly not being critical of any coach who is out there talking about energy system training, but what I'm trying to present to you is the best explanation of energy systems as they relate to climbing performance, given the latest research and understanding of what's going on in hardworking muscles. That's what I'm going to present to you. It's not based on dogma of the past. It's not based on 20 or 30-year-old exercise physiology textbooks, which have some things wrong, we've learned here. Science is really never settled. We're always trying to explore and come to new realizations and understandings, and sometimes the old science is proven wrong. And that is definitely the case with some aspects of this subject of the bioenergetic systems that facilitate exercise and human locomotion. And I guess I could go off on one short tangent. So let's say start tangent now. And that relates to the term lactic acid. It's a term which is virtually ubiquitous in the lexicon of athletes and coaches. I used the term a lot in the past. A A lot of coaches in and out of climbing, a lot of climbers and athletes in various sports talk about lactic acid, blame their muscle fatigue on, quote, lactic acid. Some even blame their muscle soreness, like delayed onset muscle soreness that occurs a day or two after exercise or climbing. Some blame that on lactic acid, and it's all wrong. Forget about it. But it's still kind of a contentious topic. However, the consensus of sports scientists have come to understand and embrace the idea that lactic acid really doesn't occur in the body, not at biological pH. It really is 99% dissociated in the blood, in the cytoplasm of human cells. Outside of the human body, it may associate and be lactic acid, but within our body, it's 99% dissociated into lactate anions and protons, which are hydrogen ions. And so there is a correlation within the muscle of the development of lactate and these protons, but only one of them you might say is kind of bad, and the other is actually quite helpful. And so let's first talk about lactate, and we'll talk later in the podcast, we'll be talking quite a bit about lactate, but in a nutshell, it's a byproduct of anaerobic glycolysis. And it's actually a metabolic bridge from the anaerobic energy system to the aerobic energy system, because lactate can be oxidized within the mitochondria via the aerobic pathway. And so lactate itself is not a bad thing. It's even now recognized to be a signaling molecule, so that when you have high lactate levels in your working muscles, it signals some of the adaptations that we're after, like angiogenesis, the development of new capillaries. Muscle hypertrophy is believed to be signaled by high lactate content, and even perhaps wound healing or muscle or tendon healing is signaled by high lactate content within a working muscle and in your bloodstream. Now, the one bad thing is the protons, which result in acidosis, which is a lowering of the pH of the cytosol inside the working cell and eventually in the bloodstream. And that lowering pH threatens homeostasis and contributes to fatigue one way or another. And again, this hasn't been fully elucidated, but it certainly interferes with mitochondria and their ability to produce ATP aerobically, and perhaps even has effects on, an afferent effect, a feedback effect on the central nervous system that results in a reduction in neural output and a reduction in force output, kind of a self-protective mechanism. So there you go, lactic acid, remove that term from your vocabulary and instead talk about lactate, or talk about the protons or the hydrogen ions that are kind of the bad guy in the whole equation of things. End tangent. Okay, so moving ahead, the three parts of this podcast. First, we're going to do a quick review of the energy systems that generate ATP for muscle contraction, that enable you to exercise and climb and basically be alive. Number two, we're going to then drill down into the anaerobic lactic pathway. And then number three, I'll provide some guidelines on training anaerobic capacity, because that's really what we're after here with this anaerobic lactic energy system, is the capacity to generate high levels of ATP and to power high-intensity exercise and climbing for an extended period of time. Like I said, 15 seconds to a minute or two, perhaps 3. And so what we often are talking about here is training your strength endurance, like how many times you can grip small holds in a row before your high force output grip fails, and also power endurance, like those big powerful moves that you make on steep routes. How long can your muscles persevere despite the increase in those protons, or the lowering of the pH, the acidosis that's building and contributing to the burning in your muscles and the failing of your anaerobic lactic pathway. So when we're talking about training strength endurance and power endurance, it's really about increasing your anaerobic capacity. Okay, So on to part one, which is our overview of the three energy systems. And I'll tell you, these three energy systems, they are separated for the sake of discussion and learning, but really they're all ongoing within our body pretty much all the time. ATP is being generated through all three energy systems. It's really, the body has an exquisite balance and ability to turn off and on the various energy systems, or to call one more into play than the other based on power requirements. And that's ultimately what it comes down to, is what are you asking your muscles to do at any given moment? If it's high power output or low power output, different energy systems are more prominently called into play. And you'll get a better sense of that as we go through the podcast today. But ultimately, what it's all about is these three energy pathways that generate ATP, adenosine triphosphate. ATP is the donor of free energy within our muscles. It's what fuels muscle contraction and relaxation. When ATP is split, energy is released, and that's what allows muscle cells to contract and relax. For powerful movements, you need to split a tremendous volume of ATP very quickly. For just sitting around watching TV, you don't need to split ATP so fast. You just need to keep your various organs and functioning and your muscles relaxed, but on call to act in an instant. And that's what is very interesting about these different energy pathways, is the ability for them to turn off and on very, very quickly, and your body's ability to prolifically reproduce ATP at very, very high rates. Here's a fantastic statistic. It's really kind of mind-boggling, but it's been calculated that within one day, your body recycles an amount of ATP approximately equal to your body weight. So think about this. Those little ATP molecules are generated or recycled through these three energy pathways to create a volume of ATP equal to your body weight. Now, it's a recycling process. The food you eat is ultimately what provides the substrate for the generation of ATP, but your body is designed to rapidly resynthesize ATP at a very high rate if you're an athlete. And if you want to be a better athlete, you have to train and adapt to create ATP at an even higher rate, that's called power, and for a longer duration, which is capacity. If you have robust ATP production, well, then you're likely a healthy, fit individual. And here's something interesting. If you have poor ATP production, especially if your mitochondria are not functioning well or beginning to dysfunction, that is tied to a myriad of diseases and disorders. And generally, if you can't produce ATP well, you're probably a pretty ill person. And so in being an athlete and keeping these energy systems functioning and humming at a very high level, there's definitely an effect in terms of your longevity and your ability to live life with high energy. And that's important because success comes to the energetic. Okay, so on to pathway number one, just a quick recap. The Atp-Cp system, also called Anaerobic Lactic energy system, that's what the first episode of this energy system series looked very closely at. And it's certainly difficult information to grasp on the first listening. You probably would benefit from going back and listening to that podcast a couple more times to learn how to train anaerobic power, because that's what we're talking about here. The anaerobic alactic energy system is what yields the fastest rate of ATP production for maximal power output. So when somebody's talking about training anaerobic power, it is this energy system that they should be training, at least if they know what they're doing or if they want to actually get results. And in any case, when you begin intense exercise, about the first 1 second, there's ATP that is resident, ready to go, instant on, that is split. And then almost immediately, creatine phosphate stored within the cell is split to donate a phosphate for resynthesis of ATP. And so for about the first 5 seconds of intense all-out exercise, resident ATP and CP are what energize your activities, your contractions. But by about 5 seconds, the very high rate of splitting of ATP into ADP and an inorganic phosphate, those rising levels of ADP and PI, which is the inorganic phosphate, are a signal for glycolysis to begin, for the anaerobic lactic energy system to begin to kick in. So already 5 seconds into intense exercise, 5 seconds into a sprint, 5 seconds into a set on the campus board, 5 seconds into a maximal boulder problem, glycolysis begins to spin up. And by about 10 to 15 seconds, the anaerobic alactic energy system has pretty much run its course, and you're into anaerobic glycolysis taking over. Like I said, from 15 seconds onward, high-intensity exercise is largely fueled by ATP generated via the anaerobic lactic pathway. So again, it's important to recognize how these energy systems significantly overlap and to some degree complement each other, but also, as you'll learn, perhaps can interfere with each other. And you'll see how that occurs in just a moment. Okay, the second energy pathway is that anaerobic lactic energy system, or the glycolytic pathway. And in this case, it's muscle glycogen, which is stored sugar, granules of stored sugar in the cytosol of the cell, and also glucose that is free-flowing in your bloodstream. They are broken down. And this ramps up, as I said, beginning about 5 seconds into intense exercise, and by 10 to 15 seconds, it's the primary pathway by which ATP is produced. At about 1 minute of sustained all-out exercise, the anaerobic lactic energy system is starting to fade, is starting to run aground, and the aerobic energy system is kicking in. And by about 75 seconds, the aerobic system becomes the prevalent energy system, the prevalent pathway by which ATP is produced. The glycolytic system hangs in out to 2, even 3 minutes, but it's fading fast as, again, that transition takes place from one energy pathway dominating to the other. And that crossover occurs right around 1 minute of intense all-out exercise. Okay, so glycolysis, you're breaking down glucose from the bloodstream and glycogen within the muscle cells. It's an 11-step process that yields either 2 or 3 ATPs per molecule of glucose. If you break down glycogen within the cell, those glycogen granules, you actually yield 3 ATP. There's one less step than if you break down glucose and therefore only acquire 2 ATPs from the glycolysis. And so you can get faster ATP production by splitting the glycogen within the muscle cell. It's immediate to where the ATP needs to be used, and it provides an extra ATP, whereas the glucose needs to be transported into the cell and then split and only yields 2 ATP per molecule. But both fuel anaerobic glycolysis. I guess early in a workout or early in a day of climbing, when you have a full glycogen stores within your muscles, you're going to have a little higher anaerobic power and capacity than later in the session when the glycogen is beginning to deplete, and adrenaline kicks in and helps enable glucose to continue a steady flow into your bloodstream and therefore into your muscle cells. But it's not quite the same rate of ATP production as what you would get from glycogen. These are still fast reactions compared to the aerobic pathway that we'll talk about in a moment. And so power output via the anaerobic lactic energy system is quite high. That first energy system, Atp-Cp, that's what fuels those bursts of power that only last a few seconds. That's anaerobic power. 100% power output for a maximal move or two. And then as the glycolytic system kicks in, the lactic system kicks in, power output is less but still high. You can exercise in that first minute or so at 70 or 80, perhaps 90% of peak power, but it's a downward slide very, very quickly, especially as that oxidative system kicks in. Power output drops quickly at right around a minute or so, and then eventually you kind of reach that aerobic steady state or critical power at around 3 minutes of sustained all-out exercise. And that critical power is only about 1/3 of the maximum power, that maximum anaerobic power. So that critical power, that peak aerobic power at 3 minutes that you can sustain for quite a long time via the aerobic pathway is only about 1/3 of the peak power output via the Atp-Cp system. That's your anaerobic power. So you can see how power output drops rapidly as you go from 5 seconds to, say, 3 minutes as you traverse the three energy systems. And the sharpest decrease in power output is right around 1 minute, give or take 15 seconds or so, depending on an individual climber's anaerobic capacity and aerobic power. Okay, on to the third energy system. It's the aerobic pathway. It kicks in pretty early on, 15 to 30 seconds into sustained high energy exercise. It kicks in. At 60 to 75 seconds, it takes over as the primary source of ATP production. By 2 minutes of sustained all-out exercise, it's contributing probably about 80% of ATP production, with the other 20% coming from the anaerobic lactic energy system. And then, as I said, by about 3 minutes and beyond, more than 90%, the vast majority of ATP production is from the aerobic energy system, which is a sustainable level of ATP production and therefore a sustainable power output that you can continue with, though at only a fraction of peak power output. So while the first two energy pathways are non-mitochondrial sources of ATP, and they are very limited in their ability to produce ATP for an extended period of time, this third pathway, the aerobic energy system, can sustain power output for a long time. Mitochondria, especially well-trained mitochondria, can generate ATP for hours, and I guess in the case of an ultramarathoner, days. So it's really quite amazing, and they are highly adaptable and can be trained up to, especially in terms of capacity, but also to some degree in power. But the mitochondrial pathway, the aerobic pathway, will never generate power anywhere near at the level, or never generate ATP at the rate that the anaerobic systems do. And that's where they are distinctly different. And as a climber and as an athlete, you need to recognize where certain energy systems tend to dominate, what your strengths and weaknesses are with regard to these three energy systems, and which one you can best train up to increase ATP production and increase your power output for your projects, whether they're boulder problems or single-pitch sport routes or multi-pitch or big wall routes. That's really the magic of taking this information and applying it. And how do you program it to get your results that you can continue to build on season over season? Again, the next podcast, next month, we will drill down into the aerobic energy system and give you a better understanding of the benefits of climbing-specific aerobic training and generalized aerobic training, things like running or biking or swimming and such. Okay, so when you consider these three energy systems, it seems like a relatively simple topic, something that is pretty easy to apply, but it's the interaction between the energy systems, the competing adaptations, and also the unique nature of climbing that makes it frustratingly difficult to really wrap your head around and decipher and figure out how to best apply to climbing. You know, climbing is not a steady state sport. It's a stop and go sport. And when you read about energy systems and ATP production and training the energy systems in books or on the internet, it almost all deals with sustained activities like running or playing soccer, or perhaps weightlifting, which is more of a stop-and-go activity, but is still quite different from rock climbing. And, what's most, novel about climbing is what's going on in the forearms. The forearms are often the limiting constraint physically when we're climbing. And the unique thing about climbing is that when you grip intensely, really if you're gripping anything over 50% of maximum voluntary contraction, you are occluding blood flow. You're stopping the supply of blood, of oxygen to the working muscles. And so if you grip every handhold for 5 or 7 or 10 seconds, you are occluding blood flow. You're going anaerobic almost instantly as the capillaries are squeezed free of blood and there's really no oxygen left to diffuse into the working cells. And so only when blood is flowing are you able to have the aerobic pathway contributing, and hence the anaerobic pathway is prevalent in hard climbing, at least when you're gripping the rock. Compare that with a runner who is turning over their legs very quickly and contracting and relaxing very, very quickly, and with every step or a weightlifter with every lift is squeezing blood in and out of the muscles. This muscle pump helps move blood through at a very regular rate to get oxygenated blood into the system, into the working muscle. And again, in climbing, we spend more time gripping than we do relaxing. If you're in the midst of a hard maximal sequence, you are gripping for longer durations than you're relaxing, often at a ratio of 7 to 1, let's say 7 seconds of gripping to 1 second of relaxation. And so you have these ischemic periods, these periods where there's no blood flow and you are going anaerobic, and ultimately that leads you down this path of rapid fatigue. And so you can't just take energy system training or understanding as recommended for runners and apply it to climbing, because climbing is a truly novel sporting endeavor with novel physical stresses and bioenergetic constraints. And so this is something that I've really worked hard the last few years to sort out, and I'm still in the process. I'm not 100% there, but I think I'm well along the path, and the material I'm presenting to you here, while maybe not 100% right, I think is very much on the right track, and I would hope represents the kind of the state of the art or the state of the science for training for climbing. And so these three energy systems are constantly contributing to different degrees, often depending on not only power output, but on whether there's blood flow or not through the working muscles. And climbing researchers are starting to look into this. There's been some studies done on bioenergetics of climbing, and specifically the forearm muscles. I'm doing some of my own research, collecting data, doing lactate testing and finger force testing and muscle oxygen testing, and these things are helping me better understand what's going on, and all of this I think will build in the coming years. There's an exciting conference this summer I'll be speaking at. It's the International Rock Climbing Researchers Association meeting in Chamonix, France in July, and I'll be speaking there on this subject of energy system training, and there will be other researchers presenting their papers on a variety of subjects, but some of which involve these topics. And so that's going to be a rich time for exchange of ideas and cutting-edge research, and I suspect a lot of coaches, especially European coaches, will be there. And I think there's a coaches roundtable planned where we can exchange ideas and talk training protocols, and boy, I'm psyched for it. It's going to be fun. Okay, so that's it for part one, the overview of the three energy systems. And now we move on to new territory, which is our drill down on the anaerobic lactic energy system. So I've said it once or twice, and I'll say it again. This is kind of that intermediate energy pathway that bridges the high-energy phosphates that are stored in your cells, the ATP and Cp, and the aerobic energy system. This anaerobic lactic system dominates from 15 seconds to 60 seconds of intense all-out exercise, and it fades quickly after 60 seconds. And by about 3 minutes of sustained exercise or climbing, it is a small contributor with the oxidative pathway dominating. Most climbers quickly come to recognize that when they fail on a route, when their forearms are pumping out and their power output is dropping rapidly, they recognize that this is the energy system that seems to be failing them. Now, it's not quite that simple, but that's not a wrong conclusion, but it's only part of the story, and that's where we have to kind of unravel how these energy systems interact. So here for a moment, I want to give just a brief look at the biochemistry of what's going on with the anaerobic lactic energy system. And I am not a PhD in biochemistry, so please forgive me if I get some of these details wrong, but I think I have a pretty good understanding of it. And, that first energy system, the Atp-Cp system, at about 5 seconds into maximal power output, that's anaerobic power, the rising levels of ADP and PI, those are the byproducts when you break down ATP, and also increasing intracellular calcium ions are all believed to signal the glycolytic system into play, that anaerobic lactic pathway to begin to fire up. Anaerobic enzymes begin to upregulate that will enable the breakdown of glycogen and glucose, specifically the enzyme PFK, which is phosphofructokinase, and that PFK enzyme is what catalyzes the breakdown of glucose and glycogen and allows ATP to be released. And the result of glycolysis is a molecule called pyruvate and also hydrogen ions or protons. And so this is where things get interesting, and also some dispute remains among exercise physiologists when it comes to the pyruvate and the hydrogen ions and what role they play going forward. But the one thing all sports scientists agree on is that the hydrogen ions and the resultant lowering of intracellular pH begins to interfere with that PFK enzyme. And so as ATP is produced rapidly via this anaerobic lactic pathway, the rising proton load and the lowering of pH begins to interfere with the key enzyme PFK. So in that sense, it's a rate-limiting or rate-controlling enzyme, and I guess it's the body's protective mechanism that this enzyme being interfered with by these protons prevents the pH from dropping too low. It's a protective mechanism to maintain homeostasis. Fortunately, your body is able to buffer some of that acid and take on and deal with those protons. One of the adaptations, or a few of the adaptations that you're after when you train this energy pathway, is to improve the buffering and the transport of these metabolic byproducts that threaten homeostasis and that ultimately limit your power output during those 15-second to 1 to 2 minute bursts that you have to make through a hard crux sequence. Anyway, your perception of increasing fatigue and the very real drop in power output that you experience, it's largely peripheral fatigue occurring within the muscle cell, due to this loss of homeostasis, due to that anaerobic lactic energy system beginning to run aground. But there may also be some central control, afferent signals from muscle to brain. The nervous system is likely downregulating neural drive, again, as kind of a protective mechanism. In my book, Training for Climbing, I have a whole section on the role that the central governor, kind of this black box in your brain, exerts on limiting power output. It's a really rich topic for maybe another podcast, but I want to resist a tangent and continue to move on here. In any case, in terms of your desire to persevere, to have greater anaerobic capacity, to sustain high power output longer and longer, there's adaptations we're after, but there's also actions you can take to limit the fatigue and allow homeostasis to be maintained a little longer. One of them is to keep blood flowing through the working muscles as much as possible. Again, this concept of when you grip the rock intensely at more than 50% of peak finger force, you completely occlude blood flow. And this obviously cuts off oxygen supply and any support that the aerobic pathway can contribute to ATP production. But in doing so, it also prevents your body from taking that pyruvate and oxidizing it in the mitochondria. And so as long as you're breaking down glucose and glycogen in an oxygen-starved environment, this pyruvate byproduct cannot be oxidized by the mitochondria and therefore has to be dealt with in another way. And that other way is the generation of lactate. Now, in doing so, the pyruvate, along with the NADH, takes on a proton to create lactate. And in this way, acts as a buffer. Now, the cytosol inside the cell has its own buffering system. It's kind of a first round of defense against lowering pH. But that intracellular buffering plays out very quickly and is very limited. And although it can be trained up somewhat, the bulk of the proton load has to be handled through this process of generating lactate and transporting it out of the cell. And so the generation of this lactate is a good thing. And as I mentioned earlier, lactate actually is a bridge to the aerobic energy system, because if you can get it out of the working cell, if you can get it out of the fast twitch fiber, which is where this lactate is mostly generated, if you can get it into the bloodstream or into a neighboring slow twitch fiber, it can be oxidized and used as fuel. And so that's a pretty cool thing, how the byproduct of the anaerobic energy system can be used as a fuel for the aerobic energy system. And I'll talk more about that in just a moment. But the most important thing is that when you are squeezing a hold, when you are contracting in a very powerful way, the ischemia and the hypoxic environment means that only the anaerobic energy pathway can be at work, and resultant rapid release of protons lowers the pH. And if there's not blood flowing, that intercellular pH will drop rapidly from a normal pH of around 7 inside the cell down to perhaps close to 6. And eventually, anaerobic glycolysis shuts down, because homeostasis has been so severely threatened. And that's when you notice power output or muscle cramping or just the end of climbing. You know, you're yelling, take, because you just can't generate any force anymore. So from a climbing perspective, you want to limit how long you maximally contract on holds. That's one of the secrets of Adam Ondra, is his high rate of climbing. He only grips holds for a few seconds at a time, whereas a slower climber might grip holds for 7 or 10 seconds. Adam grips holds for 2 or 3 seconds. You know, the presentation that I'm going to present in Chamonix at the Researchers Conference is a breakdown of both Adam Ondra's ascent of silence and Margot Hayes' ascent of biography. I have the film. We're actually going to do a video breakdown and take a look at how quickly they both climb, how precise they move through their crux sequences, how efficient they are, and how remarkably brief they grab each hold, thus limiting time under tension, thus making those periods of ischemia, of hypoxia, so brief, and allowing brief bursts of blood flow through their muscles between grips that slows the acidification of the muscle cells and allows kind of this flushing, this movement of lactate out of the working muscles and to other parts of the body that can deal with it. And again, by striving to preserve homeostasis, they're able to sustain high power output longer. In any case, the bottom line is that this high-intensity exercise, especially if blood flow is occluded, is limited to a very brief duration. and power output, especially if you're gripping hard, will drop sharply from 20 seconds to 30 seconds to 40 seconds through a maximal sequence. Whereas if you can keep the blood flowing, you may be able to persevere for 50 seconds or 60 seconds or beyond and exhibit or express a higher anaerobic capacity. And that's what Andra and Hayes do on their ascents of those two very difficult routes, is in moving quickly and keeping blood flow going, they're able to maximize their anaerobic capacity. And as it turns out, when you watch the film, all of the crux sections of their respective climbs, they do in about 60 seconds or less before that anaerobic power output drops off a cliff. No pun intended. So in any case, they exhibit this high anaerobic capacity that is ultimately the result of the fact that they keep blood flow going, keep the oxidative system at work to kind of support the anaerobic system by removing those byproducts, by keeping the intercellular pH closer to normal, and getting the lactate and other metabolic byproducts out of the working muscles. So again, it's complex stuff. Sorting out these energy systems and just how they apply to climbing and how you can leverage this information to perform better is really complex stuff, and it's why these podcasts get so long, and I guess this one's really turning into a stem winder, huh? So in any case, it's a subject that will continue to kind of unlock in the months and years to come. And I think, as I've stated in previous podcasts, when this is fully realized and elucidated, we will take training for climbing a few years from now to a whole nother level than where it is at now, with most people training in ways and with protocols that are a decade or more old. We're trying to move things into the future, and this is one of the key topics to get us there. Okay, so back to what is going on inside of the cell. There's this anaerobic glycolysis occurring, providing this ATP production, this rapid flux of ATP for you to sustain high power output, but the byproducts are pyruvate and these hydrogen ions. And if there's oxygen available, well, the pyruvate, at least a portion of it, can be oxidized in mitochondria. But if your gripping holds and you have this lack of blood flow, essentially an oxygen-starved environment, well, then thankfully we have this metabolic process that takes pyruvate and along with an NADH, consumes a hydrogen ion, and converts and generates lactate. And it's catalyzed, by the way, by an enzyme called Lactate Dehydrogenase, or LDHA, that facilitates the conversion of pyruvate into lactate. And then the lactate can be transported out of the cell by a lactate transporter called MCT1. And this protein is something that is upregulated by way of anaerobic lactic training. So these enzymes like the LDHA and the lactate transporter MCT1, these are things that you are trying to upregulate and have expressed by way of effective anaerobic lactate training. And we'll talk about the protocols and the ways to do that in just a moment. But if we can get this lactate out of the cell, and by the way, it's co-transported with a hydrogen ion, and so in moving lactate out of the muscle cell into the bloodstream, it takes a hydrogen ion with it. And so that helps limit the acidosis within the working cell. And then you have this diffusion gradient. Blood, the pH is tightly controlled between about 7.3 and 7.4. So you can move that hydrogen ion into the bloodstream and circulate it. And of course, the blood has its own buffering, bicarbonate, that comes into play to help maintain the blood pH within that tight range that I mentioned. So there's a lot of moving parts here and a lot of nuance to how this is all operating. But the more of these players that you have operating, these enzymes and these lactate transporters and these buffers, the more you can spin them up, the higher aerobic power and capacity you will be able to express in climbing. And so those adaptations are really what you're after when you're training. Just a quick comment about what happens to the lactate once it exits the cell into the bloodstream. I mentioned that it can move on to a neighboring muscle cell, an oxidative fiber, to be oxidized by mitochondria and therefore become a fuel for ATP production via the aerobic pathway. It can also circulate to your brain and to your heart. Those are organs which can use lactate as fuel, a very effective fuel. And ultimately, there's the Cori cycle where the lactate circulates back to your liver and through gluconeogenesis is converted to glucose in the liver, which can then be recirculated or stored as fuel for later use. And so our bodies are quite remarkable in how these energy systems can recycle and again, continually replenish themselves. Sure, we need to be able to eat some food along the way, but for short-term exercise, an hour or two, there's no food you need to eat to keep your energy going. If you're running an ultramarathon, yes. If you're going climbing for an hour or two, no. You don't need to consume much fuel until after the workout. And one more comment before I move on. Having a strong aerobic energy system, not only climbing specific, but generalized, allows you to metabolize lactate more quickly. And there's some research that has shown, and I've mentioned this previously and written about it in my book, that aerobically trained climbers, those who do some generalized aerobic training, recover more quickly because they're able to deal with these metabolic byproducts more readily and are able to use lactate as fuel and help lower blood lactate levels more quickly. So when you're resting between climbs or even resting on a climb, a more aerobically fit climber will recover more quickly. So it just goes to show that you really can't be a one-trick pony. You can't rely on one energy system. I guess if you just specialize in 5-move boulder problems, or if all you ever do is the campus board, well, then you can focus on maybe just training high-energy phosphates, that Atp-Cp pathway. But if you're doing rock climbs that last longer than 15 or 20 seconds, and certainly if you're doing roped climbs, you need to bring all 3 energy systems up. That should be a goal of your training, a comprehensive program to elevate all 3 pathways for generating ATP more rapidly and for building out your capacity to generate ATP, massive amounts of ATP during a climbing session or a training session. And so you need to keep that in mind, not do just one type of training, but be able to cover all your bases and ultimately try to spin up all 3 energy systems. Now, I mentioned earlier, you can't be great at everything, and that's where each individual, based on their projects and their strengths and weaknesses and even age and genetics, needs to determine which energy pathway is the gold for them, which one's going to get them to the next level, and perhaps focus on one system to train up more than the others while trying to keep all 3 balls in the air, trying to keep all 3 systems up to snuff. And that's the magic of exercise program design and is really difficult to pull off. But for an elite climber, trying to eke out the next grade is essential to do. Okay, so there's a long-winded explanation, kind of the science behind this anaerobic lactic energy system, but I feel it's important to have some background understanding of all the different players that are at work to help support ATP production through this pathway, because it's such a crucial energy pathway for pushing your limits and for high-end, high-power output bouldering and climbing. And so I guess if you can grasp onto some of this science, it will hopefully compel you to follow through on a more specific, more nuanced training program, and so that you just don't walk into the gym and do what you've always done, but try to be more thoughtful in your training, be more precise in the exercises you do, how long and hard you climb or train, how long are your rest breaks, that nuance. Simple things like work to rest ratios while you're climbing or training are crucial for bringing about certain adaptations. And so that's where the next part of this podcast is going to go, is what types of protocols, what types of training can you do to increase your anaerobic capacity? And again, anaerobic capacity is how much ATP you can produce in a given period of time. With regard to all-out climbing, you're usually talking about 60 seconds to maybe 2 or 3 minutes at the most, because the aerobic energy system takes over as the primary source of ATP production after that. So think of anaerobic capacity as how much work you can do, how much power you can express into the rock. How many hard moves you can do in a row in 60 seconds, in 90 seconds, in maybe 2 minutes of all-out climbing before your muscles fail you and your power output just falls off that cliff, and you can only continue at a much lower intensity supported by that aerobic system. That's what we're after in the training. Now again, there's support from the other two energy systems, but if you're going to train this right, if you're going to train the anaerobic lactic system effectively, you need to target it as precisely as possible. And that's where we're going, but I think we're going to do it in a separate podcast that will be released back to back with this podcast, or maybe just a few days apart. I want to try to keep these podcasts under an hour from here on out to keep them not so long and overwhelming. And so this podcast is going to end now, and you can queue up the next podcast to get into actual exercise protocols for training up your anaerobic capacity. And then we'll wrap up this podcast with a few comments about programming your training, and we'll set the stage for the next energy system podcast, which will delve into the aerobic pathway of ATP production.